Hello, everyone. I'm Samantha Pilgrim, and today I'll be talking about my research in finite approximations of C-star algebras. Just a little about me. I'm a PhD candidate in the math department at UH Manoa, and I'm receiving the 2021 Sarah Ann Martin Arcs Award in Mathematics. I study the abstract mathematics that underlies much of physics, especially quantum mechanics and quantum information theory, and much of that research involves C-star algebras, a mathematical object that encodes the evolution of physical systems. Many of these objects are infinite dimensional, so it's important to know when we can approximate them by finite dimensional objects that are easier to understand. And the language of mathematics makes this precise, but also obscures how really intuitive some of the ideas are, so I'll just try to give some geometric intuition. Symmetry is a fundamental concept in mathematics, and one way to talk about symmetry is through the language of groups and group actions. So to give a nice accessible example, let's think about the circle and imagine rotating by a fixed angle theta. We say the integers act on the circle because we can think of each integer n as corresponding to rotation by that angle n times. If theta happens to be irrational, then we never come back to the same exact place no matter how large n is, but that rotation is approximated by a rational rotation that will come back to where it started after finitely many applications. Let's just see an illustration of that irrational rotation. You see we make a hash mark everywhere the blue marked point lands, and the hash marks never land exactly on top of each other again. So my conjecture in general is that many types of symmetry that involve rigid motions like rotations or reflections can be approximated by finite symmetries like the example just discussed. And I've proved this in a couple of cases now. For example, one can also think of symmetries of Cantor sets that preserve distances. And these can be thought of as symmetries of sort of an infinitely branching tree with finitely many vertices at each level, as I've have pictured here. This is important because many C-star algebras arise out of group actions, and finite approximations of the group actions can be used to infer finite dimensional approximations of the C-star algebras. And understanding the structure of those is really important for a lot of physical problems, especially if you want to understand a quantum mechanical system or like how different kinds of energy are propagated through different media. This is very important. So that's all I have. Thank you for your time.